Vamos, listo. Hola, bienvenidas y bienvenidos al coloquio de investigación del mes de abril. Hoy contamos con la participación del doctor Sarira Sajú, quien es investigador titular, tiempo completo, del Departamento de Física de Altas Energías de nuestro instituto. Es miembro del Sistema Nacional de Investigadores, nivel 2. El doctor Sarira obtuvo el doctorado en astropartículas en Utkal University, India, y posteriormente realizó diversas estancias postdoctorales en España, India y México. Ha realizado diversas estancias sabáticas, recientemente en el reconocido Instituto de Investigación Riken de Japón, becado por la Sociedad Japonesa de Promoción de la Ciencia. Además, ha realizado estancias sabáticas en India, en el Laboratorio de Investigación en Física. Ha realizado también más de 60 visitas a centros de investigación de diversos países. Cuenta con 67 artículos de investigación en revistas indizadas de circulación internacional, 24 memorias en extenso, ponencias en 113 congresos internacionales, ha participado en 48 simposios y escuelas y ha dirigido 2 tesis de doctorado, 6 de maestría y 5 de licenciatura. Entre sus líneas de investigación se encuentran astrofísica de neutrinos, rayos cósmicos, física de gamma ray bars, física de partículas elementales en plasmas relativistas. El día de hoy nos presentará el coloquio de investigación titulado Multi-Messenger Astronomy, Very High Energy Gamma Rays and Neutrinos. Sarira, please go ahead with your presentation. Please share your screen.
Okay.
And welcome.
Ok, ¿está bien?
Sí, adelante.
Ok. Hola, buenas tardes. Voy a hablar en inglés. Entonces, por favor, quien tiene problemas, púntales y yo puedes preguntar después de mi charla. Okay. I am going to talk about multi-messenger astronomy, very high energy gamma rays and neutrinos. And in this talk, I am going to talk about these two important messengers, like, for example, high energy gamma rays and neutrinos. I'm not going to talk about low energy gamma rays and low energy neutrinos. Only this is related to high energies. Okay. So what do you mean by messengers? Basically, you can see that messengers like a postman or somebody brings message from one place to your place. So that is what messengers is. So in this case, the messengers, what we mean by is that the things or entity which brings and deliver information to the recipients, and that is what messengers is. So basically it brings information from other places. Like, for example, you get information from the sun by light, whatever information it gives, or electromagnetic wave. Similarly, the cosmic rays, which are the particles or which are the high energy particles produced in some astrophysical or cosmological scenarios. And these particles comes to us. When we detect them, we get information about the source, about their energies, and many other things. Similarly, neutrinos also are produced in nuclear reactions. And these neutrinos can come from the source to us. And when we detect them, we will get information about the source. And recently, in the last 2-3 years, we have interesting information about the gravitational wave, which is basically telling about the collision of either two black hole, one neutron stars, or extreme condition in the universe where they are producing gravitational waves. So all these probes or messengers bring information from the source by giving us different type of informations. Like for example, you can also, here you can see the sources are sun, galaxies, collapse of a star, gamma ray burst, Big Bang, and many other things. Okay. Really, all this information which are coming, all these messengers which are bringing the informations, what do we learn from them? We learn basically many things. For example, mechanism of particle productions, how particles are being produced, all these high energy particles, I mean, mechanism of particle productions, matter content of the source, because every matter cannot produce all these high energy particles. So it depends on the type of matters also. And acceleration mechanism, what are the process which produces these accelerations? So powerful acceleration, because this is unthinkable in the present day technology on Earth, that we can have this type of particles. Okay. Energy extraction mechanism, how do we extract energy, or how these particles are getting energy, so much energetic in this process, that also we learn. And working of the universe, so how really universe works by producing this type of particles, propagating this type of particles, what are the mechanisms and all these things. And overall also we learn about dark matter in the universe, because if these particles are coming and they may interact with this dark matter, so whatever you expect, you may not expect that, you may not get that one because of the dark matter. Or if there is dark matter and this dark matter is particles are very heavy, they may decay, they may annihilate, and they may produce high energy gamma rays. So this may also tell about the dark matter in the universe. Okay, so to start with, let's see in the universe what normally we see is, we see the normal visible light, and you see here, Antonio, can you see my pointer?
Yes, we can see the pointer, yeah.
Okay. So this is the very small, you see, this is the complete scale, or you can say see in terms of wavelength here. This is the complete wavelength. Here, only this little bit we can see. This is the one which our eyes can see. And from to the left and to the right, this we cannot see. Okay. So basically, to understand the universe, understand the functioning of the universe, we need to understand, or we need to know how the universe looks in low energy or high wavelength, or high energy and low wavelength. So this is what. So basically what I am telling is that we have to understand or we have to see different types of frequencies or different types of wavelength to understand better the universe. So you can see this, what are these scales in the radio wave, what we can see, in microwave, what we can see here, and infrared, visible light, and all these things. So basically, to our eyes, most of the universe is not visible. We don't know. Actually, by whatever you see, maybe this world looks so beautiful with this very little bit of windows, but this most of the things are not visible to us, or probably we cannot see them. So that is what different type of instrument are there to detect these wavelengths, or detect the universe in different energies and wavelengths. Okay. Now going to the more fundamental, if you don't know, let me tell this universe, or basically matter, this matter what you see around, or you and me and everybody, whatever is there, what you can see, visible universe, they are made up of protons and neutrons and electrons. And these particles, well, basically protons and neutrons, they are not fundamental entities. in the universe, or in the sense that if you break them, they are made up of something else. For example, in this universe, what physicists or particle physicists, they see is that there are three families. So one family, here you can see the quarks, one family, two family, and three families. So basically, if you see our visible universe is made up of U quarks, D quarks. Mostly protons and neutrons are made up of U and D quarks, then electrons, and then electron neutrinos. Okay, these are the, well, neutrinos for the time being, forget that. But our universe is really observable universe is made up of U quark, D quark, and electron. That's all. And these things are produced, well, photons are produced, but these things, all these rest of the things are produced when there is collision. But in normal sense, our universe is made up of up-down quark and electrons. But these up-down quarks, they make protons and neutrons and electrons. So these are the things which are made up of our universe, and rest of the things are produced as a byproduct when there is collisions and all these things. Then if you see in the natures, our interactions are governed by different type of interactions, which are basically called electromagnetic. Then it is strong force, then weak force, and gravitational force. So these are the things, and where in the modern terms of particle physics, forces of when particles they interact, they exchange particles among themselves. For example, when electromagnetic interactions, they exchange photons or light particles. When there is weak interactions, they exchange particles which are called W and G bosons. And when there is strong interactions, they exchange among themselves. There is another type of particles which is called gluon. And in gravitational interactions, they exchange gravitons. Okay. Okay. But this okay. All right. Now let's go to the next one. Okay. Now we are talking about the astrophysical messengers or cosmological messenger, whatever you tell. They are coming either from our galaxies or outside of our galaxies, which is basically, you can tell that cosmological. These particles bring really huge amount of information, which if we can detect them, then we will get enormous amount of information. For example, let's say this is the source which is producing protons, photons, neutrinos, and many other things, many other particles. But these are the particles which they can come to us and give us information. But it is not that easy that these particles are produced and they simply come to us. There are many hurdles. There are many problems when they are coming on the way. For example, if you consider, if you see the Big Bang theory, which tells that how our universe was produced from a point, then in this Big Bang theory, it tells that after 380,000 years of the Big Bang theory or Big Bang, the electrons and protons which were formed, they start coupling to produce the hydrogen atom. And during that time, or before that, the photons or the light was with them. They were just interacting among themselves and they are perfectly okay. But when hydrogen atom starts forming, that time these photons started decoupling, or the temperature was started going down, and slowly these photons decoupled from that, and then the system was transparent to that. So these photons were not interacting, they were left alone. And because the universe was expanding, these particles, these photons, their temperature went down to thousands of degree Kelvin. And today, the temperature of these photons, which is called the cosmic microwave photons, is 2.7 degree Kelvin, which is very small, 10 to the power minus 4 electron volt, 7 times 10 to the power minus 4 electron volt. So this is there everywhere. It is there. It is there in your room also, from where you are listening to this, or everywhere it is there. So these are there. And these photons, or these light particles, you can tell, microwave light particles, microwave, which are very low energies, when any particles, like for example, high energy cosmic ray protons, or any other things, or even the high energy gamma rays are coming, these are these cosmic microwave photons will interact with them, and they will give a break to them. So if they are very high energy, or they are coming from very far away, they cannot come to us. They, for example, high energy gamma rays, when it is coming from far away and very high energies, they will interact with these low energy photons, cosmic microwave backgrounds, and produce electron positron pair. So these high energy gamma rays cannot reach us. If this is a proton, then these protons will interact with this cosmic microwave background photons and produce other nuclear particles, for example, delta resonance, which is a delta particles. And again, we cannot see these high energy protons reaching to our Earth if the distance is quite far. So these are the things which one has to understand. Whereas neutrino is a particles which is very interesting, and I mean, by neutrino itself is so interesting and so complicated and confusing particles that it needs many seminars. But whatever that may be, these neutrinos are the particles which can come directly. You can see there is a straight line from the source to the Earth, and neutrino is there, these new particles, and they can bring a lot of information. So it is interesting to see these particles. For example, I will just give one example. In the sun, these photons or light particles will take millions of years from the core of the sun to reach to the Earth, whereas this neutrino will take maybe maximum around 8 minutes from the core of the sun to Earth. So if we detect this, then we can get a direct information. Okay, so that is what it is interesting. Okay, and okay, so now this Big Bang, which I was telling, it started from some points, and then once the Big Bang was created, then slowly after millions of years, or 380,000 years, what I told, it started forming the hydrogen, and slowly it started forming galaxies and all these things. And presently we are here after about 14 billion years, and now the present universe, what it looks like, it started from this place. Okay, and this is the 380,000 years. This is the cosmic microwave background which was formed, and this is because the universe is expanding. The temperature of this one is decreasing, which is probably, I think I have in the next slide. Yes, okay. So now, so this looks like this. In the cosmic microwave background, they have detected very precisely, and this looks like this, and these red dots and all these things these are structures. So there are fluctuation in temperature, which is basically related to the structure formation in the universe, like galaxies and stars and whatnot, everything. Okay, so this is the one. Now, this curve which is I am showing here is basically the one which is the prediction of the theory. You see, these are experimental points, and this is the theory. So theory predicts so precisely. Okay, precisely. So this is the one which is cosmic microwave background peak, and this is baryon density oscillations, and these are other things which tells, but it is, you see, it is perfectly fitting. So it is fantastic. Okay, now detection of high energy particles on Earth. So this is a photo that I have shown you. So this is the cosmic rays coming, hitting somewhere else and producing showers. which we can detect. So you can see such a fantastic photo. Okay, now high energy, let us first dedicate our time to the high energy gamma rays, and then afterwards we will talk about neutrons. High energy gamma rays, very high energy gamma rays or high energy gamma rays, I mean here it is above 100 GeVs, which we normally talk about, very high energy gamma rays. But you can come down little bit, let's say few GeVs, 30 GeVs, so it is there, okay? Now, these high energy gamma rays, there are special type of detectors to detect this. For example, okay. For example, there was a detector called HEGRA, high energy gamma ray astronomy, but this has not already upgraded, and its name is MAGIC measure atmospheric gamma ray imaging Cherenkov telescopes. So this one is in La Palma, Canary Islands, Spain, and it has two telescopes. Each one is 12 meters, and now they have done the much more upgrading, and it has a range between 30 giga electron volt to 100 tera electron volt. So this is the energy range where it can detect. And similarly, there is another one is called HACE, which is in Africa, Namibia, and it has also similar range. Okay, then there is another one is called Veritas, which is in USA, Arizona, and the latest technology one is the HAWK, high altitude water Cherenkov detector. It is in Mexico, close to Mexico City, not very far away. Those who are not in Mexico, so for them, and those who are in Mexico, of course, they know quite well. And these three, first the MAGIC, the HACE, and Veritas, they have efficiency very low because they only work in moonless night, only in night, and that too in moonless night. Whereas HAWK telescopes or HAWK detector, you can tell it has a duty cycle of 24 hours. It has no problem, all these things, and it is made with different technology than the rest of the things. So which I am not going to talk about, but you can see in many places. Okay, this is one of the benchmark of Mexico was what we see, and now it is giving also very interesting results. Probably you might have seen in many news or in internet about this. Okay, now let's go how we detect this very high energy gamma rays. Basically, very high energy gamma rays comes from some source. We don't know from where it comes, but let's say it comes. Then if it is coming, then it interacts in the upper atmosphere or somewhere else, let's say, but basically it is in the upper atmosphere. It produces, interacts, and produces a lot of particles, secondary particles. You can produce electron, positrons, and muons, anti-muons, whatnot. It will produce a lot of particles with low energies, and then from this primary interactions point, then it will spread out. So it will spread out. You can see basically this angle you see, and this is now, if it is few kilometers above us, then it will produce a big shower. And these photons, these low energy photons, can be detected by these detectors, what I told, whether it is MAGIC, HACE, or HAWK here. Okay, so we can detect these. Now, so this is a detector which is the MAGIC detectors. You can see, so beautiful looking, and these are huge detectors, and these are always, for example, this is in La Palma in Canary Islands, Spain. HACE detector, there is a comparison between this and this tower from Pisa, just to show you how these fascinating looking these have. and these Verita detectors. So these are the detectors where this detects all these particles. And this is the Hawk. Now this Hawk detector is basically water tanks, okay? Water tanks, and it has fitted with different type of instrument to detect when the light passes through, or the charged particle passes through this one. They will produce Cherenkov light, and which are detected by the detector which is sitting inside each of the water tank. And this is okay, this is the one. Now sources of very high energy gamma rays. As I told you, this is the most important things. We have to know the source. What type of sources are producing these high energy gamma rays? Well, we can first start with active galactic nuclei, which are basically, most of them are having a supermassive black hole sitting at the center of the galaxies, and it is eating, everything is going into this one. In the process of going in, these particles, they will produce lot of thermal, non-thermal particles, like for example, photons or protons or electrons. They will produce this, and some of these particles, we can see them. Well, of course, we will not see once they cross the event horizon, because after certain distance, the particle goes, means it goes. You will not see them. But all these things, whatever we see, is just before that, much before that. Okay, so that is what we see. Okay, so this is the one which produces a lot of these high energy gamma rays through different processes. And then second comes the gamma ray burst. This is another thing, but here it is not a supermassive black hole. It is a black hole of order, let's say, 30 to 40 mass of the sun. But this is such a tremendous event, which produces in few seconds, it produces like whatever energy billions of suns, trillions of suns will produce, it will produce in 1 second. So maybe this is what is called the, after the Big Bang, this is the most energetic or most powerful things which takes place, gamma ray burst. And it is interesting to know that almost every day we are seeing around I think around 1 to 2 gamma ray bursts in the universe. There are detectors which are detecting them, and that means what it tells is that these gamma ray bursts are produced because there is a formation of black holes. So in the universe, every day there are formation of black holes. Then pulsars. Pulsars are also objects which are basically, when a star dies, a small star which is not as big as this 30 to 40 solar mass, smaller than that, then many times they are end up with a neutron stars. And these neutron stars, they are basically, when they are become old, they become pulsars. And then decay of dark matter. Dark matter, as I told you in the introductions, that when suppose the unknown type of particles which we don't know, which are, we believe that they are forming dark matter, if these particles are very heavy, then they can decay, or they can collide with the particle antiparticles of their natures, and then they can produce high energy gamma rays, which we can see. Okay, so these are the basically sources of high energy gamma rays. Now we have seen that among these active galactic nuclei, what I told, this has many subclasses. It has divided into many classes. One of them is a blazar, which is very interesting. And I am going to talk a little bit about this one, because last few years, most of my work is dedicated to this high energy blazars. Okay. Now you see, this is the classification of high energy blazars. So active galactic nuclei, sorry. And in this, there are so many classifications, but forget about all these things. You don't have to worry. You just see, this is the one which is one of the most interesting things, high energy blazars, because From here, we see really a lot of high energy gamma rays. So that is why it is interesting, and I am going to tell about little bit more about this one. Okay, now you see, when you see different classifications, for example, this is okay. Here, this sky blue, you can see this blue one is the high energy blazars. Then it is intermediate energy blazars. Then it is low energy blazars, and this is FSRQ, and this is another one called extremely high energy blazars. Okay, so these are different classifications, but you don't worry about all these things. You just see this blue one. This is what is interesting from the point of view which I am going to talk about. Okay, now, so what is a blazar? Now, question is, you just saw the classification, but we don't know what is a blazar. Basically, if you consider a active galactic nuclei, then this active galactic nuclei can be somewhere else. Whether it is producing particles or not, we don't know really, but how we will know to this is something very interesting. For example, let's say this is an active galactic nuclei where there is a supermassive black hole sitting here, and matter is accreting into this one, or it is eating all this matter. So these are really stars and whatever the planets, you can, so many things are there. So this is eating. You might have seen the photo of Milky Way. So this black hole is eating everything. So when it is eating everything, okay, it is producing thermal, non-thermal particles, and at the same time, what it is producing is, this is producing two jets. Okay, so choros in Spanish, what they call. So this jet, so matter is falling into this one, and some matters are ejecting out in this way, and these are almost perpendicular. These jets are almost perpendicular to this accretion, this or matter which is there, and this jet is coming like this, and this is the black hole. So here the particles are accelerated because of different mechanisms. So basically, in these jets, you will get particles are coming out. Then magnetic field is also there, because this matter has magnetic field. So some of this magnetic field will also come out. Photons are coming out, and almost everything is coming out. But now because this jet is very powerful, and it is already seen that they are relativistic, ultra relativistic. So they are actually, these are the places where you can see the motion of particles in very, very relativistic speeds. Okay, relativistic speeds. So they are coming out now, and some of these particles are being accelerated. Now question is that whether we can see them or not. Okay, now then the classification of this active galactic nuclei tells that, suppose by chance or fortunately, if you are somewhere else here, so this is the jet, if you are somewhere else here, then this jet is pointing directly to us, but these are far away, millions of kilometers. So you don't have to worry that this jet will kill you. No, nothing will happen, because we are millions of kilometers away from them. But if we are somewhere else here, then any fluctuation in this, or anything which is happening, we can see here directly, because we are within this cone. Okay, we are within this cone. We are somewhere else here, so we can see directly within this cone. So we can see what is going on. So this variation, fluctuation, can be directly seen by an observer if you are within this cone. And this is called, if we are within this region, then this is called blazars. If we are around this little away, let's say you can see 45 to 60 degrees, whatever that, okay, this is called quasars. And if we are somewhere else, almost 90 degrees, you can tell, then it is called radio galaxy. So this is basically the same object, but it depends where you are, because if you are here, you can directly see the fluctuation. Any high energy phenomenon can be directly seen from here. But if you are here, you may not be able to see that much. And if you are here, you are still not able to see everything. Okay, so this is basically the blazar is here. Blazar when you are here. So, and this is a system where many extreme phenomenon can take place. So it is, so that is why it is interesting. If you are here, you can see all these phenomenon, fluctuations in flux or flaring or high energy emissions. All these things can be directly seen from here. Okay, that is why it is interesting, and this is one of the main source in the universe which is producing high energy gamma rays. Okay. Okay, I think okay. Now let's see, these high energy gamma rays, when they are producing all these objects, they are normally seen, they have two peaks. One peak here in low energy, and another peak is here in high energy. So this is a traditional peak where all these blazars or active galactic nuclei they produce. Okay, irrespective of their classification, they produce this. Now, this peak, which is coming around 10 to the power 17, 10 to the power, 10 to the power 17 to 10 to the power 19 hertz frequency, this is the one which is called the first peak, or this is the one which is called, well, I mean, so this spectrum, this is called the spectral energy distribution or set. Okay. So the first peak in this region, 10 to 17 to 10 to 16 to 10 to the, or even around 10 to 15, let's say some of them are even 10 to 15, are in this region. This is called the first peak or the synchrotron peak. Why it is synchrotron peak is that when in the jet, you saw that jets where electrons are coming because they are produced and they are coming, they are non-thermal electrons. Okay, so they have some distribution, non-thermal distribution. Then when they are coming, and as I told you also, there is a magnetic field there. Then in the magnetic field, normally what happens is that when a charged particle like electron is going, then this charged particle will not go straight, it will be going some other ways, you can see here, and they will emit photons, light. Okay, but light of different frequencies, and these photons, they will go, but then it depends on the magnetic field, and it depends on so many things. So it so happens that around these regions, these photons are produced more, and then they have a peak here. Okay, so this is the one, this is the first peak. The second peak is coming now. Okay, sorry. Okay, the second peak is coming here. The second peak is coming here because see, the electrons are coming and they have a power law like this. They have a, I will try not to use a lot of equations. I will just tell whatever is necessary. So this type of dependence is called power law, where alpha is equal to or greater than 2. So this is called power law. So they fall like this. If you plot, if you plot them, then they will fall like this. So what happens is that the higher energy electrons will interact with these low energy photons, and by inverse Compton scattering, like for example, this is the high energy electrons, this is the low energy photons of this one, these photons basically, but here in this region, they will kick this photon, and the photon will take the most of the energy of the electrons, and they will be going with higher energy, and there will be a second peak. So this is called the inverse Compton peak, or this process is called the inverse Compton scattering process. So the higher energy electrons will produce this one, lower energy electrons will produce this one. So this is the set. Okay. Now, what happens? You might have seen that sun has a 11-year cycles, where sometimes this sun during this 11-year cycles, this can have very intense emissions. Magnetic field may be very high, and the flaring, it can also flare. So this is something called flaring. So you can see, so this type of things happen. So you imagine that in the type of object we are telling these blazars, they are millions of times bigger than this one. So you can imagine that, so how tremendous it will be. So during that time, but we don't know really how the flaring takes place or why it takes place, but we know that there is a flaring going on, and during this process, what happens is that apart from this second peak, there are higher energies photons are produced, or gamma rays, which are few hundred GeVs to TeVs. Gamma rays are produced. So these gamma rays are produced, and one has to know really what is the mechanism which is responsible for that one, and that is what we want to understand, and that is what is interesting in here. Okay, now as I told you that when the particles are produced, high energy particles are produced in the source, and they are coming to us, but on the way there are so many difficulties for them. For example, cosmic microwave background, when the protons or photons are passing through that, then they will interact, because they will not allow, they will act as a filter, then they will not allow very high energy gamma rays or very high energy cosmic rays to pass through, and they will interact with them and produce some other particle. Similarly, what happens is that apart from cosmic microwave backgrounds, after the when the galaxies start forming in the universe, then because of the nuclear reactions in these galaxies, they produce a lot of light of different frequencies, and this light is there. It is like cosmic microwave background is there everywhere. This light is also there everywhere. Okay, and these lights, for example, if you see here, this is the cosmic microwave background peak, which is there. Then this is cosmic infrared background, cosmic optical background, ultraviolet, X-rays, gamma rays. All these lights are there. All these are there everywhere. Well, okay, their numbers may be small, but they are there. So when our high energy particles, it is here in these photos, you can see, suppose from AGN, a high energy particle is, photon is coming, or gamma rays is coming, this gamma ray will interact with these low energy photons, cosmic infrared background, optical or UV, depending on the energies, and then they can produce a pair of electron positrons. Okay, so by producing electron positron pair, now the high energy gamma rays cannot reach to Earth. Okay, so basically what we are we will not be able to see very high energy gamma rays. So this is a filter which is being used now. Okay, so they are again, so if you want to measure all these high energy gamma rays coming from different sources, how far they are, one has to take care of this background. Okay, otherwise our calculation or our prediction will be completely wrong. So one has to understand that this extragalactic background light, or EBL, so to understand all these experiments. Now what happens that now let us talk how these high energy gamma rays are produced, because there are many processes. For example, very high energy electrons, okay, if they are there, then they interact with the like for example, inverse Compton scattering. I told, if the energy of the electron is very high and it can kick the photon out, so it can produce this high energy gamma rays basically. Okay, another thing is that suppose if you have cosmic rays like protons, they are coming and they interact with the proton in the background, or on the way you have hydrogen gas, okay, on the way, or you have photon in the on the way. So if they interact with them, they can produce pions. So pion is a particles which are coming in three different one is pi plus, another is pi minus, another is neutral pion. So pi plus, pi minus, and pi 0. But if we are talking here, proton interacting with the photons, so it will produce, at least up to first order, it will produce pi plus or pi 0. It will not produce pi minus. Well, if it will produce pi minus, then it has to produce more pions. Okay, so let's say it produces pi 0. This pi 0 will instantly decay to 2 photons. So this is the most favorable decay mode of these particles. So it will produce 2 gamma rays, and these gamma rays can be very high energy, and that is what we can see. Okay, Now, furthermore, if this gamma ray is still high, it can interact with other things and produce, it can interact with the background photons and produce electron-positron pair, but that is not what we are trying to tell. Okay, now, so this is one thing. And another thing, it produces pi plus. Then this pi plus will decay to mu plus, mu, and this mu will further decay to positron, electron, neutron, muon, antineutrino. So basically, what it tells is that it can produce neutrinos and it can produce gamma rays. So in this process, you can see both neutrinos and gamma rays depending on the energy of the proton, initial proton. You can have, similarly, if this is extremely high, then they can be very high. If it is low, then they will be low. Okay, so it depends on the initial energy of the proton. And there is something called, there is something also here. What happens is that I am talking about a model which is photohydronic model, which is mostly developed by us, and we are working on this one, and which I am going to tell also little bit more in detail. So this is the one where proton comes, high energy proton comes as a cosmic rays. It interacts with the photon to produce a particle called delta resonance, which I will show you in subsequent slides. And then after that, it produces all this rest of this chain. Like for example, here you see this is a high energy protons. Depends on how high, depends on the gamma rays we will see. And this is called, this is a low energy photons, which can be in the, what I told, it can be in the jet of this blazar, or it can be outside. So, but if it is outside, it is very low energy. So this proton has to be very high energy to produce the delta resonance. But if it is in the jet, depending on where it is interacting, this proton can be low energies. So to produce this p pi 0 proton pi 0, and pi 0 will instantaneously decay to two gammas. These gammas, we claim that this is the one which you see as high energy gamma rays in the detectors, what I am telling. And this pi plus, neutron pi plus, this pi plus will decay to all these four particles, and this can be absorbed on the way by interacting with other things. But these are the neutrinos which if we are in very proper directions, then this can reach us. And if they are highly energetic, probably we will be able to see them. Okay. Okay. Now, all these details I am not going to talk about because this is not interesting for you. Okay. Now, what I was telling you is that you saw that this spectral energy distribution of said it had two peaks. So these are the two peaks. But suddenly in some places they have seen that there is a third peak which is coming because of the flaring I told you. So this third peak is very difficult to explain. In theoretically, it is very difficult to explain. There are many models to explain that. Some of them, they claim that it is because very high energy electrons are coming and they are kicking the photons out and producing this third one. And there are other theories which tells that no, it is the hydrons or protons, they are coming and interacting with the photons or protons in the background to produce these things. So there are many things, but which we are going to talk about. Okay. And this is another one. This is a one which is coming like this. So these are third peaks. But whatever that theory may be, it is difficult to explain this third peak. And that is what we have our photohydronic model uses that. Now, I am not going to talk how our model works, but at least I will show you some of the, because this is a colloquium, so I want to tell more things rather than telling more detail about what we are doing. But this is our theory which we have developed, and you see our theory explains this very well. Also, this is another one, photohydronic model, we can explain this. This is another one. All these things we have explained very well using the photohydronic model. So what it tells is that basically the proton interacting with a photon in the background of the jet can explain this very well, and we are able to explain that. So this is something very interesting. Okay. Now, coming to the extragalactic background light, which I told that this light will not allow the photons of very high energy to come in. It is just to show you that, you see, this is energy of the cosmic energy of the high energy gamma rays, which is coming from somewhere else, and this is the red shifts of the object from where it is coming. Now you see, if you are nearby, which this is the Markarian 421 is the nearest high energy blazars or active galactic nuclei, you can tell. This is nearest to all. The next nearest is Markarian 501. So you can see that if you want to see, you can see 10 TeV gamma rays from there. But now if you go increase the distance or redshifts of this object, the energy will drop drastically. So if something is here, something, let's say it is 0.1, 0.2, 0.3, 0.4, 0.5. So if it is something is here at 0.5, or these objects, these high energy blazars, so basically your flux is, your energy is down very drastically. So what it tells is that if object is very far away, then you are unable to see high energy gamma rays coming from them. That is simply because, let's say this is the high energy gamma rays which is coming from the source, and this is the gamma rays, this is the photon which is in the background, extragalactic background light, and they will interact and produce electron and positron pair. So basically this high energy gamma rays will lose everything and we will not be able to see. It means that our detector will not be able to detect these high energy gamma rays if they are coming from far away or if they are very high. Okay. Okay. Now, high energy cosmic rays. High energy cosmic rays are the proton which I told you. They can be high, they can be very high, they can be extremely high. Okay. It depends on, because now we have detectors in many places to see this. One of the most important detector is the Pierre-Roger Observatory, which is in Argentina. So this detects, suppose for example, your high energy cosmic rays is coming, it interacts somewhere else here, and it produces all these particles. It produces all these secondary particles, and they can be scattered square kilometers. Okay, so and these particles can be detected by these detectors. Now, okay. Now I will tell you about the Pierre-Roger detector later on, which I have some slides. Now here what is happening is that, for example, to detect this type of particles, we need detectors of huge size. For example, here you see it is low energy, 10 to the power 9 to 10 to the power 11, let's say, or 10 to the power 13. In this one, you will get, or maybe here, this yellow one, 10 to the power 9, below that, electron volt, you will see 1 per meter square per second. So it's a huge number of particles are coming. But now you go from here up to here, you will see here, for example, you see 1 per meter square per year. So it has drastically down. Here, 1 per kilometer square per year. So here, if you go to 10 to 19 to 10 to 21, you will see that number of particles, or even in this one, you will see that number of particles, what you see, or cosmic rays you will see is drastically slow or drastically small. So that means if you want to see particles in this region, maybe you have to, if you put a tank here, then probably you have to wait for 100 years so that a particle high energy cosmic rays will come and hit. But we cannot do that. So what one has to do is that either you take a detector which is 100 times bigger than this one, so that you can wait for 1 year, or you can take even much more bigger than this one, so that you can see few events per year. So that is the idea. And here it is compared with a leg. You can see this is called knee, this is called ankle, and all these things. So because this spectrum behaves in this way, So that is what they have put. Okay, but the idea is that to detect these extremely high energy particles, we need extremely huge detectors. Okay, otherwise you will not be able to see. So that is this lower energy part of this one. So these are the detected points where this is there. And now to show this, I think it is here. Okay, so this is the detector, Pierre Rosette detectors, which is in Argentina. I told this is a 3,000 square kilometer detector, so it's a huge size. Okay, huge size. And so we can see at least few events per year. Okay, if we are lucky. Otherwise, if you have a very small one, it is almost impossible to detect this. And this is how they generate this. Suppose, for example, a high energy particles is coming, it is hitting somewhere else here, and it producing all this shower, and these showers are detected by these detectors. Okay, so this is another one. Well, this is the bigger picture of the Pierre Rosette Observatory, and how they see these things. So this is okay. Now let us come to neutrino astronomy. This neutrino astronomy, as I told you, that neutrinos are particles which can come directly from the source to the detectors, like for example on Earth. Whereas if you have proton coming, proton will also bring information, but protons are charged particles, so they can be deflected in the magnetic field when they are coming. So if you detect a proton, it is not necessarily that it is coming from the source to which you are thinking. It may be coming from somewhere else. So it depends on the energy and magnetic field, so many things. Then photons, as I told you, these high energy gamma rays are coming. They may be interacting also. Apart from that, sorry, these protons are they can be deflected by the magnetic field. But if the protons are extremely energetic, high energies, then these protons can interact with cosmic microwave backgrounds to produce another secondary particle. So we will not able to see. So basically, what it is telling is that these protons have difficulties in reaching us because of the magnetic field, because of their energy and all these things. On the other hand, the gamma rays, which are although photons, which are although neutral particles, they should come directly. But as I told you, this extragalactic background light or cosmic extragalactic background light, mostly they will interact with these photons to produce electron positron pair. So they may not come from far up, or very high energy gamma rays, they may not reach us. So we will not know anything about the source if the energy is very high. Of course, low energy photons will come, but low energy photons will give you different information. Okay. Then another one is the neutrinos. So neutrinos are being neutral particles, and they are weakly interacting. So they will almost not interact. For example, they can penetrate through the galaxies, or they can penetrate through the Earth very easily. Okay. So you have to be your experiment has to be very precise to detect them, or out of few millions, maybe we will be able to detect one neutrino. Okay, if we are lucky. So that is what. But if we detect these neutrinos, it will come directly from the source. So you can see really it is coming from there, and it can give us very valuable information. Now, before going to this neutrino astronomy, let me tell you a little bit about low energy neutrinos. This is a detector. This is called the Super Kamiokande detector, and this is one is called Sudbury Neutrino Observatory. This is in Japan. So this is a huge detectors, and this is almost 2 kilometers underground, and this is a boat where they are putting all these photomultiplier tubes. Okay, and to detect this. Okay, and this is also having a similar technology, and they can detect low energy neutrinos. Basically, they are meant to detect the neutrinos from the sun. Okay, and which we have already seen with precision. They have seen that. And there are other sources, for example, nuclear reactors. Nuclear reactors, they can also produce neutrinos. Like sun, they can also produce neutrinos. And well, this is not, well, here I want to tell you that for example, all these Sudbury Neutrino Observatory or Super Kamiokande, they can detect neutrinos directly, whether it is in the night or it is in the day. Actually, when they are in the night, because night you are in the opposite side of the sun, so neutrino will pass through the earth. Whereas in the daytime they will just come from your above you, but in the night they will come directly from the opposite side of the earth. So because as I told you, this neutrino can simply penetrate through low energy neutrinos. So you will be able to see this neutrino if you detect them. And they have already seen these neutrinos in the daytime and night times, which is very precise, which is very interesting. Okay. These are good pictures of this Super Kamiokande. I just wanted to show you because they are fascinating. Okay. Okay. I think it is not necessary. So this is something very interesting, dancing of neutrinos. So what do you mean by that? Well, so far we know the particles, the protons, the electrons, the neutrons, not neutrons, exact neutrons. Forget about neutrons, protons and electrons. These are the particles which, whatever they are coming, they are coming. But this is a particle which is very, very terrible, very, very strange particles. Neutrino is a very strange particles. They oscillate in the sense that here you see one, then maybe if you go few million kilometers or few thousand kilometers, the same particle will change. Another few thousand kilometers, maybe this will change. So they are coming in three flavors: electron flavor, muon flavor, or tau flavors. So depending on where you are, you may be seeing different type of neutrinos. So that is what it is called, the oscillation of neutrinos, which was and this oscillation of neutrino was from the neutrino observed from the sun. We have seen by this detector, Super Kamiokande and Sudbury neutrino observatories, that neutrino do oscillate. Okay, that is experimentally verified. Okay, so now what happens? There is another one called atmospheric neutrino. I showed you this figure previously. That high energy cosmic rays are coming, and they are interacting in the upper atmosphere, and they are producing pions. Okay, so now forget about this pi 0 because it is producing gamma rays. Let us not talk about this one because we are talking now neutrino, and this produces three type of neutrinos. Okay, so these neutrinos are also observed on Earth, and if they are exactly whatever the way they are producing, we should see two muon neutrinos. Muon neutrino means muon and its antiparticles, and one electron neutrino. So we should see in a ratio of 2:1. But that is, we have not seen that. That is because these neutrinos are oscillating. That's why we have not seen 2:1, but we have seen different. Then there are other neutrinos, little higher energy neutrinos. They are called supernova neutrinos. But just to show you this one, Antonio, how much time I have?
Yes, I think that 5 minutes, if you could.
Okay. So then I will not go to this one. Maybe my extremely high energy neutrino messengers from heaven. So this is something very interesting. You should, I mean, this is for those who are interested. I think they should hear this one. So this is, you see, all these particles, high energy particles, whether it is a cosmic rays or it is a neutrino, it is difficult to detect. Actually, it is very difficult to detect them. And you need huge detectors. But huge detectors need huge amount of fundings, huge amount of money. So this is not only a financial problem, it is also a technological problem, it is also a problem of space. So to detect these high energy neutrinos, physicists came with very innovative ideas to use ice as a detecting material or detector material. So they wanted to fish or capture neutrino in ice. So the best place to do this is in the South Pole. North Pole is because most of the population in the north area, so maybe this is a little bit polluted, this ice. So North Pole is much more fresh and pure. So then they constructed neutrino detector in the South Pole. So this is a neutrino detector which looks like this. This is the surface, and this is you see this is the height depth of this detector, which is around 1450 kilometers below, up to around 303 kilometers. So, and for comparison, they have shown the Eiffel Tower. You can see. So these are the, so they have put strings, steel strings, and in this they are putting the detectors which is hanging there, and using this one as a detectors, they have detected neutrinos. So this looks like this. So there are 86 strings, 160 ice top tanks, which is we are not interested. And these are the detectors, 5,480 digital optical modules, which are these circular things. Okay, so they use this one. You can see how much money and all the, how many people are working this one. You can see this one. So these are the one, and this one, this light which are produced by passing neutrino and interacting with the matter, they will produce this secondary light which will be produced here, which will be captured here, and we can see them. So this is one of the event. This is a event which they have seen. Okay, let me not talk about this one. And so this is another event which they have seen. This every high energy event has a name. You can see this name here. So they have seen this one, and these are the events they have seen. Energy, this is the energy, and this is the from which direction they are coming. They have seen this. So mostly you see this is below 100 TeVs. Most of them, these events are below 100 TeVs, but there are some events which they have seen very high energy events. And recently there is a paper published in Nature last month. So they have seen a event which is extremely high energies, which was seen in 2018, I think December 2018, which is very interesting. I don't have time to talk more about that one, but well, so these are, when they see these events, they see from which direction they are coming. As I told you, these neutrinos, they can come directly and hit. If we are lucky, they will hit. So from there we can see from which direction they are coming, and with some certain amount of errors, we can see from which direction they are coming, and is there anything in that directions which is active. So that is what they are seeing this, and these are the objects from around which they are coming. And there are something very interesting happened in 2017, that they saw one neutrino event which name is IceCube 170922A. This is the year, this is the month, and this is the date. If they see more than one, then they put A, B, C, whatever that. Okay, so this is coming from a blazar called TXS 0506 0506 plus 056. These are catalogs. They put these names, so you don't have to worry about this one. And they saw this event, and during that time, this object was also in a very high state, and they saw this is the first direct evidence that blazars are, or high active galactic nuclei in generals, are sources. They can produce very high energy neutrinos. So if they are producing high energy neutrinos, as you saw, that these high energy protons or high energy cosmic ray they are coming, they are producing pi zeros, pi plus, and also they can produce pi minus, but when they are producing a lot of pions. So this pi zero can produce gamma rays, and pi plus can produce neutrinos. So that means what happens is that, so there is a correlation between high energy gamma rays and neutrinos. Okay, so if they are seeing these things, that means they have to be coming from very high energy or extremely high energy cosmic rays. So then in the Earth, we have both all these three types of detectors: high energy cosmic rays detectors like Pierre-Roger, then high energy gamma ray detectors like Hawk or Magic or Veritas. Okay, and then we have neutrino detectors like IceCube, what I showed. So these things, they can be detected, and in future we will be able to see these three types of events simultaneously, almost simultaneously. Then we can verify that what is the source, from which directions they are coming, and we will be able to tell about these sources. Again, recently they have seen some high gamma ray burst, which according to the theory that they should also produce very high energy gamma rays like few hundred GeVs to TeV gamma rays, but they had not seen that one. But since 2018, they have seen two events, and another one they claim, but it has not been published. So one of the events they saw, this is the one which I think they have seen in 2019, and this you can see that these photohydronic interactions we could able to explain this data very well, and also some other things we are able to explain this very well. So it shows that now we are going, okay, to last one, the IceCube saw this extremely high energy neutrino events, 6.3 peta electron volt event, which it is produced last month, 10th of March. They tell that this is called glasso resonance, which is very important, which they were looking for, and they have seen. So what it shows, all these things shows that we are in a very interesting time, and we have also very good technology to detect all these extreme phenomena in the universe and to understand the universe much better. So those who are interested to do physics, they should think now that it is the right time for them and the right technology, so they can really understand so many things, and we can understand universe in a much better way. Previously, it was not known to our previous generations, but now it is time to think and to join this type of physics, to work in this type of physics, so you can contribute to the understanding of the nature in general, and very specific things also you can understand, and you can have a valuable contribution to the development of science in Mexico in particular, or in the world in general. Okay, so this is okay. To summarize this, all these signals hints towards extreme phenomena in the universe. For example, active galactic nuclei, gamma ray burst, or hypernova. These are basically death of massive stars. Okay, knowing the source will tell us about the type of objects and phenomena responsible. And this will also help us understand the fundamental mechanism and their operations in nature. So it is very important to study all these things. And as I told you, it is right time to join this type of works. And finally, let me thank you. So this is what I have put. This is something which I put. It has very good significance. Let me give a minute. It is in Madagascar. These trees are called baobab. These trees, they can survive for thousands of years. Okay, and because thousands of years they are surviving and they are seeing the universe, so that's why I put this one here, thinking that they can tell the stories of the universe, and they can understand better than us because they are seeing this universe for a long time. Okay, thank you very much.
Thank you very much, Sarira, for this nice presentation. Let me check whether there are some questions. There is one question from Wolfram Hittenholz. Are the photons from blazars with 10 to 20 TeV still considered a puzzler? They could generate electron-positron pairs and inverse Compton scattering, but the energy threshold seems to be tricky.
Can you repeat the question, please?
Are the photons from blazars with 10 to 20 TeV still considered a puzzler? They could generate electron-positron pairs and inverse Compton scattering, but the energy threshold seems to be tricky.
Well, from blazars, because they are far away, you will not able to see this. First of all, 10 to 20 electron volt gamma rays will not be able to. We will never be able to see this. And of course, if they are produced there, then they will produce these electron-positron pairs with the background photons, and also they will produce inverse Compton scattering. So basically what they will do is that they will produce showers of low energy particles, like for example MEV photons, let's say MEV photons, or energy of electron positrons, but they will be distributed. But we will not be able to see these extremely high energy photons, at least from blazars. But if they are produced in our galaxies, maybe we will be able to see them because there is no extragalactic background light to block them. But still, when they are produced in 10 to the power 20 electron volt, in the source itself, they will produce electron positron pair, and I think it will be very unlikely to see this unless these photons are produced close to our atmosphere and then interact with this our atmosphere to produce the shower. Otherwise, I have no hope to see this.
Okay, there is another question from Lucas Nellen. He said that you focus on protons as high energy cosmic rays. How does the presence of nuclei change the hadronic mechanism?
Well, you can also think of this other, like for example, iron nuclei or other light nuclei. You can see that. But in that case, what will happen is that, for example, when you are talking about protons or extremely high energies, 10 to 19 or even more than that, they have a, there is something called GZK cutoff. So these proton interact with cosmic microwave background. They will produce secondary particles, okay, delta resonance, then subsequently they will decay. But this type of cutoff will be different for different type of particles. For example, iron nuclei, this will be different. Okay, so yes, we can consider that one higher this nuclei with for example iron or another light nuclei, but they are, in that case, the threshold will be different and their predictions will be comparatively different. How different, I cannot tell, but there will be different.
Okay, thank you. I don't see any other question in the chat. Is there any other question or comment? Okay, it seems that this is not the case. Then I want to thank you, Sarira, for this nice colloquium.
Thank you, thank you. It was a pleasure to be giving a colloquium.
Okay, thank you to everybody. Talk to you in 1 month with the colloquium that we will have in March. Okay, wait a moment. Wolfgang is saying that he was referring to radiation from blazars that were detected already, like Mark Rarian 500-01 is still considered a puzzler. I mean,
recently the highest energy photons they have seen from microquasars SS4433, I think, which is something around 200 TeVs. But photons, I don't know which one he is referring to. Photons, they have not seen 10 to the power 20 electron volt.
Okay. There is one comment from Lucas. He said that the observations suggest that nuclei dominate at high energies.
It's possible. Possible, yes. What Pierre Roget tells that in higher energy, nuclei dominates. I agree with him.
Okay, let me wait a bit more. Is there any other comment or question? I don't see any additional question. Then thanks a lot, Sarira.
Okay.
Okay, thank you.
Okay, thank you very much. Just before that, well, I am just seeing this chart. I was referring to radiation from blazar that were detected already, like Markarian 501 is still there considering. Well, again, this Markarian 501 maximum energy they have seen is, I think, around 26 tera-electron volt, high energy gamma rays, or 30. I don't remember exactly, but it is not more than 30 or 35 tera-electron volts, because you will not be able to see from Markarian 501 high energy gamma rays because of this distance. Because you see, when you take this EBL, their optical depth, they will go down very fast. So you will not be able to see any high energy gamma rays above 30 to 40 TeVs. It is impossible. Well, probably in the next generation detectors, if they have, and they can collect huge amount of photons, then in that case, they may go 1 or 2 orders of magnitude more in flux. Otherwise, it will be almost impossible to see at least above 35 TeV gamma rays. This object, particularly because I have around 3 papers on this object, so I know quite well about this object.
Okay, thank you.
Okay, thank you.
Okay, I think that it's time to close the colloquium. Thank you.
Okay, thank you. Thanks to everybody.